Hi, in this video, we're going to take a look at generalized linear models for the purpose of supervised learning. So our goal here is to go through either like regression or classification or possibly multinomial classification with a linear model. And what we're going to do, we're going to assume that we have an exponential family distribution going on, and we are going to fit a generalized linear model. Now, a generalized linear model is a model that uses an exponential family distribution in its theoretical assumptions. And these are pretty flexible from like a statistics point of view. These are not as flexible as, let's say, like random forest or stochastic gradient boosting or neural network or something like that. But these are pretty flexible. Also, generalized linear models can actually be part of the activation function or link function, depending on how you look at it, of neural networks. And so a link function from generalized linear models is the inverse of an activation function when we're doing neural networks. So if we want to understand neural networks, we really need to start by understanding GLMs first. Now, from this point of view, we're just going to have we're not going to have a hidden layer. We're taking all of our inputs and they're going straight into the link function, the inverse of the activation function to get things going. All right, so why would we use generalized linear models? Well, first and foremost, they're pretty flexible. They can handle, a pretty decent range of problems for regression and classification. Also, they have nearly as much interpretability as multiple linear regression. They're a little bit more complicated most of the time, but we still have the interpretation aspect of coefficients that I'd like to have when I'm dealing with multiple linear regression. Also, these are widely accepted. All right, so a lot of the times our stakeholders will have already seen multiple linear regression in a psychology class, in a business class, social science classes, a lot of places, whether it's education or pharmaceutical or whatever range, we're doing our data analysis for, a lot of times our stakeholders have already been exposed to regular multiple linear regression. And so if we present a model that looks a lot like multiple linear regression, they're going to be more prone to accept our model because they feel comfortable with it because they're familiar with it. You're going to encounter stakeholders where if I don't understand it, it must be wrong. It's going to be the position that they take. This is a very frustrating position to be in when you present some good, solid results, but because they've never seen it before, they assume you're wrong. Communication is key to getting your model to be used. And so if I have stakeholders who have seen a little bit of statistics when they were in college, maybe never even used statistics after they left college, after they took that one course, it's a good idea to, try to use a model that jives with what they're comfortable with. Because if I present something that they go, hey, I remember that from school, they're going to be like, oh, I remember that. I feel more comfortable with this than me doing something really super complicated. Even if it's a lesser performing model, if they accept it better, my model will get used, my model will have a larger impact because it'll actually, have some results, in my organization. Also, linear models, linear regression, logistic regression, generalized linear models, we can use relatively small data sets, small number of observations and be able to get a decent model. Compare that to things like neural networks or random forest, stochastic gradient boosting. I need more data to be able, more observations to be able to get a decent model going, while the linear regression models and generalized linear models, I really don't need that much data to get things going. A decision tree, I can actually pull off, more with less data, or I can pull off the model with less data. Bayesian statistics, I can actually build a model with no data at all using all priors. But, this is some of the lightest data requirements possible. All right, so we've got three components to a generalized linear model. There's the random components, there's the linear combination, and there is the link function that is the inverse of the activation function in neural networks. All right, so we can represent the situation like this. All right, so we have our expected value. So this is the expected value given our predictor variable values. G is our link function, and then here we have our linear combination. All right, so the random component in a generalized linear model specifies the distribution of the response variable. All GLMs use some form of exponential distribution. The most common distributions are Gaussian, that's the normal distribution. This one is for regular old multiple linear regression, binomial for logistic regression, Poisson distribution, gamma, which I've never actually seen launched into production professionally, but it definitely could, nothing's stopping it. Inverse Gaussian, when we have a non-negative skew right targets, and Tweety. Now, Tweety I've seen used in insurance when we had zero inflated values. That's where I've seen it used the most. Now, the linear combination forms the core of the model. It's essentially a weighted sum of the predictors. All right, so now it's a weighted sum, not weighted average, a weighted sum, because the coefficients don't have to add up to any particular value, and they can be positive and negative. In fact, they potentially could be zero. But I've got my intercepts, I've got coefficients for the first predictor variable times the first predictor variable, coefficient for the second predictor variable times the second predictor variable, and keep on going until I get to my last predictor. All right, so eta is the linear predictor. Beta 0 is the intercept or bias, if I want to call it that, like that for neural networks. The other betas are coefficients, and the x's are the predictor variables. Now, the link function provides a connection between the mean of the response variable and the linear combination of the predictors. And so when I say mean here, I'm saying this is the conditional average. So this is the conditional average of my target variable given the predictor variable values. And so G of conditional mean is equal to eta. It essentially relates the expected value of y to the linear predictors. And depending on the distribution of y, various link functions can be used. Unfortunately, when we're working in scikit-learn, I don't have a whole lot of flexibility with the link functions. There's more flexibility in stat models, and there's way more flexibility if I go into R. But the ones that are in scikit-learn are good default link functions for this purpose, and usually they do pretty well if I'm in the situation for using these generalized linear models. All right, so like I just said, scikit-learn really does not offer much flexibility in terms of the linkage of generalized linear models. All right, so like for example, I haven't seen a way to do probit regression with scikit-learn yet. Now, most of the time, logit for a binary target is going to do nearly as well, even when I've made a mistake in my hypotheses. But there's just kind of a shortcoming of scikit-learn. To me, it's not that big of a deal. It's got the major linkage that you actually want in the different situations. Now, something that is nice about scikit-learn is that we can very easily implement regularization penalties. So by default, the scikit-learn always applies an L2 penalty to generalized linear models unless it's a strictly a multiple linear regression Gaussian situation. So if I'm doing gamma, Tweety, Poisson, or logistic regression, automatically, by default, there's an L2 penalty. So it's not technically classic generalized linear models. But it's really not that big of a deal. So this L2 helps protect us from overfitting. And so the default parameters for that L2 penalty, if alpha is equal to 1, that's saying, hey, I have an L2 penalty. for these three. And when I'm in logistic regression, the default is also to do L2 penalty, but the parameter name is different and things are set up. So if I want no penalty, I want to use classic generalized linear models. I set alpha equal to 0 or I set penalty equal to none. And notice that this is the missing value none. There's no quotations on this one. And so on these three generalized linear models, I can have a penalty that is non-negative, anything from 0 to infinity. Now, if I'm doing logistic regression, I'm restricted to these four of none, L2, L1, or elastic net. Elastic net is a weighted average of L2 and L1. Now, if I want more flexibility within Python, I can go over to stats models and get that. But the focus here is on predictive analytics, where by far scikit-learn is more important for this. Stat models, I have seen stat models used professionally at work in insurance, but it's not nowhere near as common as scikit-learn. All right, so let's run through some examples. Let's load some data. So I'm going to, first and foremost, I'm going to use a house prices data set that I've already done my data prep for. This was taken from Kaggle for like the house prices advanced regression data. Now, previously I went through and did my feature selection, and I got it down to these 12 predictor variables. Practically speaking, there's very little loss in multiple linear regression or random forest if I use these 12 instead of the full data set. And now, all right, so let's go ahead and set up an X and Y. So this is all my predictor variables for every single row. Y is my target variable for every single row. So I have my training data, my validation data, my test data, and my score data are in X and Y. Now, for my training data, I'm going to restrict it to just my training data. All right, so let's go ahead and take care of the first generalized linear model, which is Gaussian regression. So this is just vanilla multiple linear regression. So it works out that if I consider the full range of possible generalized linear models under the theoretical framework, regular old Gaussian distribution, multiple linear regression falls under that umbrella. And so we're going to start here. So vanilla multiple linear regression is equivalent to a generalized linear model with a Gaussian distribution. The residuals are Gaussian distributed with mean zero and constant variance with respect to the predictors. The observed values are Gaussian distributed with a mean equal to the modeled value and the variance equal to the residual variance, the same variance I have up here. So the difference here is the residuals have mean zero, Gaussian distributed, constant variance. The observed values, so I actually see for my Y, they have mean equal to the predicted value. They're also Gaussian distributed, and the variance is the same variance as with the residuals. All right, so let's go ahead and run through an example. So first and foremost, I'm going to take a look at the histogram. So hey, I see something that looks like a Gaussian distribution. So I'm prone to thinking, hey, maybe I want to do Gaussian with this one. That's multiple linear regression. Okay, so let's go ahead and fit it. And I want to go ahead and evaluate my training, my validation, my test statistics. Fortunately, the score method makes this very easy for me. Now, typically I look at mean squared error or mean absolute error, some other way of evaluating, but because I'm using different distributions, I want a metric that's constant across the board. This score, you can think of this as a generalized version of correlation. And so this gives me the ability to compare the models I'm going to look at in a moment to this multiple linear regression that I've got right here. Now, when I compare, remember, it's different distributions. So it's not, an apples and apples comparison. It's more like apples to oranges. So, just take that with a grain of salt. It's the same measurement, but it's, I can't, when I have different data doing modeling, I can't do 100% perfect comparison. All right, so here, this is generalization of correlation. I have 0.83. then 0.88, then 0.88. All right, so what I've got here is that my validation and tests are better than training. That's an indication that I have not overfit. And I honestly would have liked this to have reached 0.9 across the board, but this might be good enough. Maybe it's not, depending on my project. All right, so the next one is the gamma regression. So if I'm looking at conditional distribution that is positive and skew right, maybe the gamma distribution is the way to go. And so in this one, all right, so how this was set up, you'll notice that when I did multiple linear regression, the expected value was equal to the linear combination. You notice that the G is the identity function on this one. My link function is the identity function. When I scroll down here for gamma regression, you'll notice I've got a logarithm around my expected value. So the log, G is equal to the logarithm, base E, and then this is equal to that linear combination. All right, so now, if you remember, I'm talking about house prices. The original house prices data is definitely positive because nobody's giving away a house for better than free. And then it's skew right because money is like always skew right anytime you're looking at it. And so I look at this, and let's say that I didn't know about, or I didn't have the option of transforming my data. So the transformation that I applied is the log, or it was the log transform. So to get back to the original values, which is up to rounding, get back to the original values, I just took e to the power of the log transformed target variable. And that's how I got this picture here. All right, so let's go ahead and fit my model. And now I'm going to go through and score it. And I'm going to do that for my train validation and test statistics. All right, so here I've got 0.82, 0.84, and 0.85. So once again, I got a little bit better for validation tests, not worried about overfitting. And now here, when I'm looking at this, realize I've got different distributions. If I would have used mean squared error here, I used mean squared error on the previous multiple linear regression model, I would have gotten two scales that were not comparable. But these are the same data. It's just how am I approaching this? And so this gives me a way of evaluating, should I use the transformation, of making it approximately, the log transformation that I ran on this data here to make it approximately normal, or should I have left it as is and use gamma regression instead? I've got both options. Well, when we look here, I had better with the transform data. So this gives me indication that it would be better to do multiple linear regression with the transform data than to leave it alone and use gamma regression. Both would have been acceptable in my opinion. Now, Poisson regression, we're going to use this when we have count data, and specifically when I have count data that sequentially increases. All right, so let's say I have an event and the count starts at 0, then it goes to 1, then it goes to 2, then it goes to 3, then it goes to 4, then it goes to 5, and so on. Typically, we're going to model that with a Poisson distribution. All right, so when could this happen? Well, let's say how many collisions were at an intersection this month. Well, the month starts, it's had 0 collisions. Then the first collision happens, that's a 1. Then the second collision happens, that's a 2. Then the third collision happens, that's a 3. And it keeps on going like this. And so something about this is that there is like a no event, first event, second event, third event, and so on down the line. This is different than counting in situations where things instantaneously happen simultaneously. So let's say that I'm rolling dice and I'm interested in the count of the dots on the dice. Well, they happen instantaneously as I roll the dice. And so there, rolling dice, even though I'm counting dots, is not Poisson distributed. So in that situation, that it would be inappropriate to use Poisson regression, even though I'm working with counts. Now, the length function, once again, is log. The difference is in the nature of the data, even though I have the same linkage. And so for this one, I'm going to use a different data set. The data set is automatically in scikit-learn's data set subportion. And so I'm going to make a function that loads the data. I'm going to load it as a data frame. And there's two data frames there. There is a target and a predictor data frame. And what I'm going to do, I'm just using concat to put them together into one data frame. Now, my predictors are weight, waist, and pulse. And then my target variables are measurements of athletic ability. So it's like chin-ups, sit-ups, and jumps, something like that. And so here, I'm just taking a look at the distribution. And so I have chin-ups, sit-ups, jumps, their weight, waist, and pulse. So the first three are target variables. The last three are predictor variables. And so now this data set only has 20 observations, so I did not do a train validation test split. I just said, hey, so I have such little data, I'm just going to run with it. Now, everything I've done so far, you'll notice that I haven't overfit on anything. As long as I'm like careful with the situation, it's not horrible to not do a train validation test split, but it would be better if I could. Typically, when I don't have too many predictor variables floating around, linear models, generalized linear models, logistic regression, with these models, as long as I don't overfit, what you see is what you get most of the time. So if I'm in a small data observation situation, I'm going to be looking to a generalized linear model first for my situation for prediction. All right, so now Tweedy regression. Tweedy regression is basically a very flexible way of fitting the model. So what I'm going to say in my hypotheses of my model, before I fit my data, I'm going to say, you know what? I think that there could be a possible range of distributions that are reasonable, all of which are within an exponential family, a range of exponential families, and I want to go ahead and fit my model. So, but I haven't nailed down the exact distribution. Well, Tweedy regression can come in for this. And so what we're going to do, we're going to have a parameter that indicates what the distribution is. And now, if I know that I want Poisson distribution, or I want gamma, or I want inverse gamma, or I want Gaussian, I'm going to go straight to those distributions. I'm not going to worry about it. But let's say that I want an exponential family that's not really quite like firmly a recognized distribution. Like, let's say I want something between Poisson and gamma. All right. Or maybe something between gamma and inverse gamma. Well, then what I can do, I can use Tweedy regression to kind of, give me what I'm truly looking for. Tweedy regression is frequently used when we have zero inflated values. So let's say I had like a gamma distribution, but I've got too many zeros in there. Like for my situation, it's either zero or a gamma distribution. That's probably going to be a good situation for Tweedy. Another one, I have a Poisson distribution, except I have too many zeros in there. Typically, Tweedy will be able to handle that for us. All right, so what I'm going to have to do, I'm going to have to decide on the power parameter of this. Typically, how I've always seen this done professionally is that we'll do a grid search to find what the best power parameter is, and here it's going to be called alpha, and then we'll go through and get it, and we can see that 0 is the best value if I'm using the score function for this. And now notice that this is only on the validation set. I'm using the validation set to determine what my parameters will be. And so then I can go through, and 0 corresponds to Gaussian distribution. So when I do Tweedy, 0 for the power corresponds to Gaussian distribution. 1 corresponds to Poisson. 2 corresponds to gamma, 3 inverse gamma, and anything between 1 and 2 is a compound boson gamma distribution. Now, I can keep on, increasing the numbers, and I can have, between 0 and 1, even though there technically isn't a distribution. I can have between 2 and 3. Wikipedia does a good job of explaining this aspect, if you want to look that up. And so, so if I look at the different alpha values, I can see what we would go with. Now, the next one is logistic regression. So this is when I have 2 levels for my target variable, such as yes, no, success, failure, 0, 1, etc. The connection to the binomial distribution is that if I have observations with exactly the same predictor variable values, and I have a 2-level target, that can be modeled as a binomial distribution itself for that one particular fixed predictor variable value combination. And so you'll frequently see, such as an R, binomial distribution for logistic regression. So that's the connection there. Now, when we do logistic regression in scikit-learn, we only have one linkage function, and that is the log odds, the logit linkage function. And so here, remember that the expected value of a Bernoulli distribution is a probability. And so this is a probability over 1 minus the probability of failure. Take the logarithms. So this is the odds of success, taking the log. So this is the log odds of it is equal to my linear combination. And so I'm going to go ahead and use the mushroom data set, which I've already done my data prep for. I've reduced the predictors down a little bit, not too far. And so now let's go ahead and fit a logistic regression model. Here is my target variable for the entire data set. We can see that we're close to 50-50, not quite. And when I go through and do my score, you can see that I have near perfect score. And so I'm not worried about overfitting. I frankly just nailed on this one. Now, the reason why I nailed it, honestly, is because one predictor variable is really, really good, odor. All right, so for your homework, take a data set that's appropriate for linear, gamma, or Poisson regression, fit a model. Then do a grid search to find the best power for a Tweedy regression and fit using the same data. Then compare your 2 models. Did Tweedy improve, or did Tweedy perform worse? Figure it out. Tell me all about it. All right. Well, that's all I've got for you. Life is short. Do math.